Good morning, everyone. A warm welcome to all of you for this webinar on brain MRI age classification using deep learning, brought to you by the Industry and Innovation Group of St. Joseph Engineering College in joint association with SJEC MATLAB. Before we move any forward, I request Dr. Rohan Pinto, Associate Professor in the Department of Electronics and Communication Engineering, to speak a few words about the biomedical projects that the students of St. Joseph Engineering College have taken up. Sir, if you could throw some light on it, please.
Yes, sir. Thank you. Welcome you all for the webinar on brain MRI age classification using deep learning by Mr. Amit Kumar, academic team member of MathWorks India. In today's world, there is a great scope for objective assessment of disorders in the biomedical field. MATLAB plays a pivotal role in this regard. MATLAB has many toolboxes which can be used for signal analysis, detection, classification, and modeling. With so many applications in the area of biomedical, we at SJEC have set up a biomedical lab in Electronics and Communication Engineering Department. We have a vibrant bunch of staff who are working under the umbrella of Biomedical Group. Few of the biomedical projects done in our biomedical lab by our students are identification and classification of brain tumor MRI images with feature extraction and probabilistic neural networks, real-time feedback system for speech therapy, prosthetic system for knee amputees, non-invasive data acquisition of ECG signals using LabVIEW, detection of cardiac murmurs using digital stethoscope, vein identification system for effective venipuncture, low-cost PROC model for ECG modeling, malaria parasite detection in the thin blood slide images, brain tumor detection using magnetic resonance imaging, smart blood tester for detection of leukemia, and many more. Today, our speaker, Mr. Amit Kumar, will be giving us an insight on the new dimension of classification of MRI images, that is, by using deep learning. With this brief introduction, I once again welcome you, sir. Thank you.
Thank you, sir. Having gone through a series of... Yes, sir. Yes, sir. Thank you. Having gone through a series of webinars conducted by SJC MATLAB, it is now time to dive into the concepts of deep learning. Today's session will provide you with insights on brain MRI age classification using deep learning. And to talk about this, we have our esteemed resource person, Mr. Amit Kamath, with us. I request Ms. Shama BN, the coordinator of this webinar, to introduce the resource person to the participants.
Thank you, sir. Ms. Ramit is an education technical evangelist at MathWorks and works with the academic institutions in India on the adaptation of MathWorks workflows in curriculum and research. Ms. Ramit has been with MathWorks for 7 years and has previously worked with the engineering development group and the software development in the image processing and computer vision areas, focusing on the workflows for image registration and pixel labeling. His areas of interest include computer vision, software engineering. Amit has a bachelor degree in electrical engineering from NIT Circle and a master's degree in electrical engineering from the University of Minnesota. Thank you.
Thank you, ma'am. I take this opportunity to extend a warm welcome to all the participants who have logged into this webinar. Without any further ado, I request Mr. Amit to kindly take over. Over to you, sir.
Thank you, hopefully I'm audible. I'll share my screen quickly so that you should be able to see my presentation as well. Please do let me know if my audio is not loud enough or my screen is not visible, in which case I will try to fix things as soon as possible. Okay. So thank you again. And for the next 15 minutes or so, we'll be talking a little bit about classifying age based off of MRI images of some study participants using deep learning, right? My name is Amit again. If you have questions that you'd like to ask after this event, please do reach out to me on my email address, which is right here. And you can find me on LinkedIn over here as well, okay? So in terms of the agenda, very quickly, I should take roughly 50 minutes. I have 5 broad topics to talk about. I will try to spend about 10 minutes each, where we'll go through some introductions about how this problem came up and how we're going to tackle it. Right? We'll then walk through some steps in solving this problem, namely how to read and explore data firstly, then pre-processing and augmenting this data, which is quite important in the deep neural network world. We'll then construct and train a deep neural network to actually try to solve this problem. And finally, it's important to explain these results, knowing that this neural network actually does something good. How and why does it do it, right? So to try to explain that, we'll spend some more time at the end. In terms of questions and answers, please post your questions in the chat or the Q&A window as soon as you think of it, because if you wait until the end, maybe you'll forget what the question was, or maybe it's not clear as earlier. So please post immediately. I'll try to track it once in a while, and if I think the response takes longer than a few minutes, I'll hold off and we can answer it later. But please post your questions right now so that you don't lose track of things, right? All right. So with that agenda, I'll quickly jump to the 3 takeaways, right? So if you forget everything else that I speak about today, I'd want you to remember these 3 things, right? The first one is deep learning has advanced state-of-the-art in medical image classification as well as segmentation, right? There are several ways you can do this, and there are non-deep learning ways of doing this as well. Just that several problems that couldn't be solved in the past as easily have now been, deep learning allows solving such problems more easily now. Right? There are several APIs and frameworks out there which help you to explore data, build a model, and train these networks. And these days, anybody working in this space in general typically is familiar with some of these frameworks, and we'll try to walk you through the MATLAB framework for today. Okay, and finally, this is very important and it's critical, I think. So there is a misconception of some sort that deep neural networks are black boxes. They are kind of closed structures that you can't understand how they work and why they work that way. This is wrong, and they don't have to be black boxes. So it is possible to explain their behavior and explain how it's working, and we'll try to demonstrate that in some time in this talk. Okay, so jumping into the first part, I'll just quickly give an introduction over on what deep neural networks are and how this came up, right? So we'll motivate the problem statement in this section. So traditionally, programming worked this way, right? So you start with some data that you want to work on, and you write a program, right? Once you have your data and you write a program, you may have to compile it for certain languages. For MATLAB, for example, you don't have to compile it. Using these 2, you run it through your computer, and then you get certain outputs, right? So this was traditionally how programming was done. Now, in the supervised machine learning world, right? So machine learning kind of twists things a little. What you notice is that the output, which was here, has now come in at the input, okay? And the program which you had to write originally is now the output of your computer, right? Is the output, it's called the model, and it's sort of the resultant of what you can build using your data and the corresponding outputs, okay? So supervised machine learning world is really creating intelligent models that are built using data and its corresponding outputs, which can then work on novel new data and then give you estimations of these outputs based on what it's learned from this data here, right? So the field of machine learning is really concerned with how to construct such programs that improve with experience, right? So really, in terms of basic definitions, right? There's a broad field of artificial intelligence, which is the ability of a, computer or an agent to perform tasks that are commonly associated with intelligent beings. Now, machine learning is a subset of artificial intelligence, which deals with, this is the formal definition by Professor Tom Mitchell at Carnegie Mellon. But really the idea is, if a program can learn from experience, can improve with more data and outputs given to it, and it can be evaluated, and we know that the experience improves over time, then such programs are really what machine learning models become, right? And deep learning is this subset of machine learning, which is the novel idea behind deep learning is really it performs these tasks directly from the data, right? So the model is learned directly from the data, could be images or text or sound or just structured spreadsheets or any kind of data of that sort that you can organize in a certain way. You could typically apply deep learning techniques on it, right? So more concretely, deep learning as applied to supervised learning problems. The difference with traditional machine learning is right here, right? So traditionally, what you have to do is you have some data to begin with, and you're trying to classify them, let's say, into what kind of vehicle it is, right? What we'd had to do in the past is we had to handcraft features based on our data, right? So in this case, for example, if we are trying to classify vehicles, maybe lines and edges are good features, right? So we handcraft these, maybe colors are good features, and we create these features from our data and then pass it through a classification model, right? This could be a traditional model like an SVM, for example, or you can do naive Bayes or discriminant, any of these types of models, and then it will tell you what kind of object it is, right? However, in the deep learning world, if you notice, there is a lot more data that we need to train on, right? And what happens here is there is no need to handcraft features anymore. The features are learned automatically. So like Professor mentioned earlier, there was a project that your students did on feature extraction, and then you did some kind of classification on it. This feature extraction or feature learning part is handled by the network itself. It's handled by this thing called the convolutional neural network in this case, and then it does the classification for you as well, right? So it is end to end, meaning you don't have to do this additional step of feature extraction in the deep learning case. However, you need a lot more data to work with to begin, right? And so the example here is for images, but you can do this for text and other types of data as well, typically. Okay. A classic such narrow AI problem is something called image classification, right? So here's a quick sort of summary of how it works, right? So if you're given an image as an input, as humans, what can we do? We can try to find out what this image contains, right? So for example, we can ask, is this a watermelon? And we'll say, no, it's not. Is this a pedestrian? And no, we'll say it's not a pedestrian, right? Is this a peacock? Yes, we know that this is a peacock just by looking at this image. And so, the image classification problem is one where the input is a color image. RGB stands for red, green, and blue. And the output is what the image contains, okay? You could have said, is this a bird? And the answer would have been correct. And so it's important to have a semantic group of objects which you choose to classify this as, right? So that's an important distinction. Now, to do this in MATLAB or to do this in a programming language, this is the artificial intelligence part, right? How do we make a program do this? It's fairly straightforward, particularly in MATLAB. You can create a network, right? So for now, think of this as a black box, right? You can then read images and show these images. You'll then resize these images to a certain specific size that depends on this network or this deep neural network here. And then you'll say, hey, deep neural network, I'm giving you this image right here, which is resized. Can you classify and tell me what it contains, right? And then the network is going to tell you that this is particularly a peacock, okay? Now, the way I've introduced this, You may think that this is going to work for all situations in all cases, right? Is that true? So let's find out, right? So let's use the same deep neural network again. Let's give a different image this time. This one's called peppers.png. It looks like this, right? We'll have to do the same resizing again, and then we'll ask the network to classify this image, right? So if the, I'll pause for a few seconds here and think about what you think the right answer in this case is, right? This is a challenging problem, right? It has garlic, it has tomatoes, it has chilies, it has capsicum and other peppers, yellow pepper, orange pepper, and so on. What AlexNet, which is this particular deep neural network, tells you is it says it's a bell pepper. Okay, so I don't know if you find this surprising. The first time I saw it, I found it surprising, and the question is, why does this happen, right? So these deep neural networks, it's not magic, right? So they have to be trained in a way, and so the deep neural networks can be, work only in situations where whatever they've been trained on, they can try to classify the inputs into those categories only, right? So, the classic example I give about this is if you have a food classifier, let's say, and you give it a completely new category of food, let's say dosa, right? You've classified other things like sandwiches and pizza and other things that are probably quite popular elsewhere, but you've never shown it a dosa. In that case, it can't tell you that this image is a dosa, right? So the bottom line really is these networks can classify into classes or categories that it has been trained on. So it can't come up with new categories on its own, right? So AlexNet, the network that I showed you earlier, was trained on 1,000 categories, of which bell pepper was one of the categories, right? So capsicum was not, garlic probably was not, right? And that's why it said bell pepper. And ImageNet, the data set has more than 14 million images, right? So this is a really large data set. And that's what makes these networks like AlexNet that I showed earlier so powerful and so interesting, okay? Right. So we'll jump now into the problem statement for this particular situation, right? So we have a bunch of MRI volume scans, okay? Specifically 155 of them. And they're of this particular size. So this is 3D now, right? So it's 79 by 95 by 68 in 3 dimensions. We also have information about the age of these participants, what their gender is, are they right-handed, left-handed, and several other parameters, right? And so the target, what we want to get out of this is we want to estimate age group now, right? So just by looking at this MRI image, can we estimate, or can we find out if the subject or the participant is between 3 to 5 years, or between 7 to 12 years, or greater than 18 years, right? So that's the kind of estimation that we're trying to make. To make this simpler, we won't use the entire volume here. We'll subsample to 2D slices, okay? So we'll only take an axial slice like this over here, and we'll only use that slice to make this estimation. You could potentially do it with 3D, but we'll do it with 2D in this case to make it simpler, right? This data comes from the Open Neuro dataset. In fact, it's available from this particular link. I'll share this presentation with you later on, and you can try to look at it from there as well. Okay. So how are we going to solve this problem now, right? So in the deep learning world, there are several steps that we typically take, right? So we start with accessing data. We then pre-process the data. We select a network or build a network. We then train that particular network on the data that we've used here. And then finally, we'll deploy it on hardware if required, right? So typically, all of these steps here are kind of done iteratively, meaning, you can end up training a network and it may not perform good enough. You can then go back to the drawing board and then redo this whole thing all over again until you get a good enough accuracy. Okay, so we'll go through each of these steps one by one in the process of this particular problem statement. Okay, so first we'll start with accessing data, right? Um, so accessing data, I'll jump into code to show you how it works. So let me quickly bring up MATLAB. So I have this live script here, which is going to help me walk through some of these steps. Okay. So just to reiterate, the problem in this particular case is we have some 3D brain MRI volumes, which we'll extract 2D horizontal slices from. We'll then train a model, and then hopefully that model should classify the age for us, right? So the first section here is we'll explore this data set, okay? So I have the data downloaded on my computer here already. It is in this particular folder called MRI root data folder, the variable here. So let me just run this section of code and show you how the volume looks like. Okay, so I'm just going to click on this blue bar here and run this code. If you notice right here, um, this is the entire one of the volumes. There are 155 of them, right? You can sort of move it around and kind of visually try to make out what it looks like. Okay. So clearly, there are some structures here within the brain that are interesting potentially. There is this, gray matter area right here. There's some white matter and all that, right? So you can visually see how this looks like, okay? There are functions in MATLAB that make it easy for you to read such data. So this, in fact, I can zoom in a little bit. This data is stored in this format called Nifty, and there are functions to read Nifty files in MATLAB, so it makes it very easy for you to work with it, right? There are also functions to show volumes. So you might be familiar with IMShow as a function to show images. There's a function called wall show as well to show volumes, which is what we saw earlier, okay? Let's go back to the presentation now. The idea is there's not just um, um, one volume, right? There are 155 volumes. So how do we deal with that, right? So this is an example of something called big data, right? So it's not just that you have one volume of a certain size. There are multiple volumes, and it is possible that these volumes do not fit in memory, right? So this is something called out of memory, or popularly called big data. And you can't just read all of them at once. And that's why we need these things called iterators, right? So there are these data structures called image data store in MATLAB, but in other frameworks, there are other similar data structures, which can help you read this data only on demand, right? So it's helpful to manage these large data sets more easily so that it doesn't load everything at once and then crashes your memory, right? So your memory may not be able to handle all of this data at the same time. And so using these data stores helps in more efficiently managing this, right? The interesting thing also, because of this out of memory kind of data management, is it doesn't have to be in your local directory only, right? These images could be on your on a file cluster, let's say, in this case, a Hadoop file cluster, right? And that's also possible to work with this kind of data because you only load it when required, right? So we can point to these images on this file cluster and load them whenever necessary, right? Cool. So that's how you kind of access data by reading those files, right? The next step is really to pre-process this data, right? So if you remember, I mentioned it's not necessary to use the entire volume. You could use just one slice, right? To make this simpler, to make this a little easier. There are only 155 participants in this study, and that may be not enough data to train networks, right? Typically, deep neural networks require a lot of data to train on. And this is a problem, particularly in the medical space, that you may not get enough data. So we'll look at how to make sure you have enough data to work with, right? So we'll look at pre-processing now, where we'll go back to code and I'll try to show you what can be done here, right? So next you can really, explore this data if you'd like. You can, uh, typically these data sets have more details about what it contains, right? So in this case, this is all anonymized, which is also another important thing in the medical space, so that there's no identifiable information. But if you notice, there is information about age. We've got age group. We've got, is this a child or an adult? What the gender is, left-handed or right-handed, and so on. There are several other parameters which you can also explore in this data set. Okay, so collecting metadata like this is important also as part of curating and building your own data set, if you like, right? So I'm just going to run this. We are also going to create these categories of ages, right? So you can do some mathematics on this on this data itself and create these categories here and find out how many people or how many subjects are in each of these categories here, right? So in the 155, we divide them into 65 children in the age 3 to 5, 57 between 7 to 12, and we have the rest of the 33 are adults. Okay. Now, the other thing you can do, which is what we'll do in this case, is to divide this or remove the 3D-ness of this data and create 2D mid slices. Okay. So we've written a function here. I won't go into the details of the function. We can talk about that later if you'd like. To create these exemplars. Okay, so let me run this and show you how it looks. You'll notice that we can create these examples of how this data looks like, and I can open this in a bigger window so that you can see it a little more clearly. So one example of a subject between 3 to 5 looks like this. Okay, and similarly for 7 to 12 and adults, we have two more examples here. Notice that there are anatomical differences in the same slice that you can make out here, right? And this is important. So if we can visually kind of explore and find out what this data is telling us. For example, these structures here are slightly different looking, right? The structures here also in this corner, I believe in these children, it's slightly larger, but then it seems to sort of shrink when people grow older, right? So you can do some kind of a visual understanding in some way of how this data looks like before you start building your own neural network. Okay, so we do that here, right? Now we'll get into actually preparing the data set for deep learning, where a typical step to do for MR data is to do something called skull stripping, right? Typically, you could also think of ways of classifying age by just the size of the, size of the skull, for example. And that's not what we want to do. We want to look at the brain structure, right? And that's kind of why we do skull stripping. And we'll do this other thing called augmentation, which we'll talk about in a bit more detail. So augmentation is this process where if you don't have enough data to begin with, you can, in some sense, artificially create more data from your existing data set itself so that you get more information, right? So one example is by flipping your images 180 degrees, right? Horizontally, you can flip them, and that way you get, another sample, right? This is very commonly done in deep neural networks because the more data you try to train your network or train your model on, the better generalization capability it has. Okay, so while I'm speaking, let me just run this and create this data store. So if you remember, I mentioned there's this data structure called the image data store, which can handle this data much more easily for us, right? So that's what we're creating at the end of preparing all of this data and applying augmentations. Okay, augmentations like this horizontal flipping, for example. Okay. So this is also really called offline data augmentation if we do it prior to training. Okay. There are online augmentation methods, which is what we do while training itself, and we'll do that later on as well. Okay. Right. So the next thing we'll do is we'll display some of these images um, uh, and just make sure that they look reasonably okay, right? So here are 3 more images that we've seen of these slices of the brain now, just to get some sense of what they look like. Okay, all right. We can also, I believe, just look at a few more here by clicking on the update button in this case, so that we'll see a few more samples and make sure that they look all right. Okay. Now, what we'll do next is to divide the data set into training and evaluation, particularly training, validation, and test. Okay. Um, this is important because in the supervised machine learning world, we want to use certain data to actually train your model. And then there are other sections of your data set that we'd like to use to validate and test. Okay. Let me just run this here, and I'll go back to these slides to explain this a little more. Okay. So the supervised learning workflow really is where you have to train your model until you find the best performing one. Okay. Generally, what happens is once you load your data, we do some pre-processing, which we've done already, right? Getting these slices, for example. And then you do the training here itself, right? So we build this model or this network, and finally we get at the output the model that's been trained on this data, right? Typically, this is done iteratively, meaning you train over and over again by potentially doing some other kind of pre-processing or by other process by which you get modifying the parameters of your model itself, for example, and you get a better and better model as you go ahead, right? Now, in the next step, to find out if your model is doing the right thing or not, we have to do this thing called testing, okay, or predicting, where you do the pre-processing step again, and then you just copy this model over on new data, right? So this new data has not been used in the training process, and then you come up with evaluations or metrics or an understanding of how well it's doing on this new data. Okay, so this new data typically is what it's used in the field, but for the process of evaluating how well your model is doing, you can actually divide your training data or your data set originally into this thing here called training data and this thing here called test data. Okay, so that's the reason why we have to split our data set. Okay, so typically what's done is a 70, 15, 15 split, right? So 70% is training, and then 15 and 15 is validation and test, right? We also do it stratified so that there's enough representation of each of these classes here in each of our data sets, right? So there's a good enough spread of ages 3 to 5 in the training as well as validation as well as test, right? So just to clarify and make it entirely clear, the training set here is used to update weights or train your model itself, right? So validation, which is right here, is used to measure the fit while training, is to measure how well your model is doing while training itself, right? And then the test set here is used to verify generalization, right? So once you've trained your model, how well does it work on this completely new data set that it's never seen before, right? So that's why the test data set is used, okay? Now I mentioned augmentation, the online and offline one. What is the intuition behind it, right? So imagine you have a bunch of training images now. The labels or the outputs for each of these training images are known, right? So we know that this is a hat, we know that this is a yacht, we know that this is a vehicle, right? you could do a bunch of these operations on each of these images. Let's say, for example, you can rotate it around, right? Or you can crop the image, or you can just maybe change color a little bit, right? When you do all of these operations, the label remains the same. The label does not change, right? It's still a hat if you do all of these processes on, right? And so by doing these transformations on your data, you now have much more data than you originally began with, right? So this process is called augmentation, and in this way, you can get much more data than you originally started, right? And this really helps in generalizing your model that you train, and it's important also, right? So this is the whole process of augmentation here, and it helps in improving your data set, the size of your data set, which in turn helps in better generalization of your models, right? And here are some very typical uh, modifications or transformations done on your data, images particularly, when you augment them, right? Okay, so that completes our pre-processing step. In the next step, we'll do selection of networks right here, okay? So I'll quickly try to walk you through what happens when a pixel goes through a classification, a convolutional neural network for the classification problem, right? So originally on the left-hand side here, you have an image right here, and then every pixel in this image goes through, a bunch of these layers. So deep neural networks are divided into a bunch of these layers, and then finally you get the a measure of which category it belongs to, right? In this case, we know that this image is a goldfish. And so, it goes through all of these layers, and then it says, okay, this is very likely to be a goldfish and not the others, right? Just to give you a sense of how these networks look like, AlexNet, the network that we demonstrated earlier, has 5 of these layers called convolution layers, okay? Which is like this, and 3 fully connected layers, right? So fully connected layers are what used to be traditionally shallow neural networks, where every neuron is connected to every other neuron, right? I'll explain what convolution layers are in a bit, which is kind of important in the context of a convolutional neural network, right? Um, AlexNet also has 62 million parameters, which is what makes it so powerful, right? So it has a lot of parameters, which allows it to learn very complex data sets and complex situations, right? So a convolution layer, right? This is really what makes a deep neural network a convolutional neural network, right? So there are other types of deep neural networks that are not convolutional, right? Like recurrent neural networks, for example, don't necessarily have to be convolutional. If this layer exists in your neural network, then the entire network is called a convolutional neural network. Okay, so it's a building block of this CNN. The idea is, imagine your original data, your input data is a 7 by 7 by 3, right? So 7 by 7 by 3 typically could be 3 is your 3 color channels, RGB, for example, and 7 by 7 are the number of pixels you have, okay? Um, what you do is you use kernels or filters of this size, for example, a 3 by 3 by 3 kernel. And so the process of convolution is where the kernel slides through the data and then does the convolution operation, right? So convolution is really sum of products, right, of corresponding pixels and the weights here. And then if you notice here at the output, um, you know, these sums of products are captured at the output right here, right? And we can do this with another um, filter as well, another kernel as well, where it also slides through our data, and then it starts sort of storing the outputs of the convolution operation here, okay? What happens after your filter kernels go through your data is we can store the outputs stacked in this format, right? And so this is the input to your convolution layer, and this is the output, and these are the weights of your kernel, right? The thing with these deep neural networks is the numerical values in these weights, they are not set by us, they are learned from the data, right? What that means is for AlexNet particularly, these patterns are learned from the data that it was trained on, which is ImageNet here, right? And so, these oriented gradients, right? You may have heard of Gabor filters, right? So these oriented gradients, it learns patterns like this from the data that it's been trained on. And that is how it can try to understand what that data contains, right? More simplistically, if you're, just as an example, if your image contains a zero like this, right? This sort of diagonal pattern, right? It is something that a kernel can learn, right? A vertical pattern right here is something that the kernel can learn. This kind of corner is also something that a kernel can learn, right? So at a very high level, what's happening is when your images go through many of these layers in your deep neural network, it keeps learning more and more complex patterns, right? So in the first few convolution layers, it learns very simple, what are called low-level features, right? So you could think of them as, if you're trying to understand a sentence, the kind of features that are learned here are how many alphabets, how many A's are in this sentence, right? So that's the kind of question that this layer is trying to answer, right? Just as an analogy, right? But as you keep going deeper and deeper into these networks, it learns more and more complex patterns, right? So here, these are simple edges and corners, but here these are combinations of these edges and corners here, right? So visually more interesting patterns. And as you go deeper, even more interesting patterns. So in the analogy, imagine you're learning phrases and so on to understand more higher level features, higher level information about that sentence, right? And so knowing these from the input data, you can kind of then make out that, okay, so, if a certain combination of these patterns exists, then maybe it's a goldfish. Or if another combination of these patterns exists, then maybe it's a cat or a dog, right? So that's what this classification part, the fully connected layers, that's what they do, okay? So hopefully this is a good overview of how these networks work. We'll jump back into MATLAB now to sort of create these networks. Okay, so there are networks that have already been pre-trained. Okay, this one's called ResNet 18. ResNet stands for residual networks. This is a family of deep neural networks that has already been trained on the ImageNet dataset. Okay, the ImageNet database right here. And so we can use this to retrain on our MR data that we have. Okay, it's very easy to sort of build and import these networks into MATLAB. It's just net equals ResNet 18. That's it, right? You can then set up a few parameters, and so I'll just run it right here. And in fact, you can ask ResNet 18 to classify one input even before we train it on our data set, right? Just to find out what it tells us. So ResNet, if you notice, tells us that this is something called a chambered nautilus, okay? You can Google what a chambered nautilus is. It's kind of a squid sort of aquatic animal, right? So clearly, the reason why this happens, just to reiterate, is that the ImageNet database has not been trained on medical data here, right? It does not know that we want to categorize into, 3 to 5-year-old children, 7 to 12-year-old children, and greater than 18. It doesn't know those categories, right? So we have to sort of modify this network to tell it that we want these 3 categories now, right? So that process of using a pre-trained network and giving it a new problem to solve is something called transfer learning, right? So transfer learning is known to be, if you use a good enough network to begin with, is known to train much faster and be much more efficient, okay? I can talk more about transfer learning later on if you're interested, but in the interest of time, I'm just going to keep going. What you have to do is modify some of the layers in this ResNet 18 network to tell it that we want to solve a new problem, right? So that's what's happening here. Okay. So, specifically, we are modifying the last few layers of this ResNet network. If you notice all the layers here, right, they're, initially they're still the same, but the last few networks here, last few layers here, those are what we modify. Okay, all right. So that is what we do there. We then can do the online augmentation as well, right? So we can randomly rotate by a certain set of angles, minus 30 degrees to 30 degrees, for example. And this can also help us give more variation to our input data, and that way can make the network generalize even better, right? So there's another data store, another data structure to handle this kind of transformations called the augmented data store, which is what we use for all the three splits, right? Training, validation, and test. We do that for all of them. Okay. So I'll just run this section here just so that we have all those variables available. Okay. Now I'll quickly go back to the slides here and show you a few more ways of constructing these networks. Okay. We have this interactive application here called the Deep Network Designer, which is a very easy way to drag and drop these layers in any configuration that you like, right? So you don't have to handwrite your own custom network if you want to build one, right? So ResNet 18 was something that we just imported that someone else had done. What if you want to create your own network, right? So one option is to build it graphically like this. You can then press the export button and then generate code out of this as well, so that you don't have to write it yourself, right? The second option is we have some helpful functions here, helpful constructors to, if there are well-known architectures, like UNet, for example, is a well-known architecture. We can construct fairly complicated deep neural networks using these functions as well, right? So this is the second option. Now, the third option is you can actually handwrite the entire network by putting together these layers, right? So remember, I mentioned deep neural networks is a bunch of layers put together. You can have convolutions, you can have ReLU, batch norm, several other layers. So this is what you'll find in most deep neural network frameworks, where you can sort of handwrite and hand construct your neural network. And that's the other option you have also. Okay. The app also allows you to troubleshoot your model. So let's say some parameters of your deep neural network are not correct, right? You can analyze these layers and find out at which layer things are not set up correctly, right? If the input size, for example, if you remember for the convolution layer, we said the input is 7 by 7 by 3, but then if in your system it's expecting a different size, you'll have to make sure that they match, right? So all of that can be computed and evaluated using this analysis application here, right? Once you sort of fix them, it'll then tell you that there are no more errors. You can then go ahead and use this network for training. Okay. So that takes us to the last but one step of actually training and testing these networks. Okay. So I'll go back to MATLAB now very quickly and show you how that's done. Okay. There are several somethings called hyperparameters. These are parameters that you can modify in the process of training, right? So they are called hyperparameters because they are modified in the process of training only. Once you finish training, there is nothing you can do about this, right? They're different from parameters. So, parameters are typically also called weights. And, the filter kernel numbers that I mentioned in the convolution layer, those are also called parameters. And that's why we have these two terms so that you don't confuse each other, right? So I won't go into the details of how we've set it up here, but really there are ways that you can sort of choose what values make sense here, right? There are, you can set up how frequently you want to validate your model, for example, using your validation data set, right? Max epochs is how many times your entire data set has to go through your entire training set has to go through your neural network to update weights, right? So 15 is what this is set to, right? And you can put all of it together into this thing called the training options here, okay? So I'm going to run this here, and that way we've put it all together and we know what hyperparameters we're using, okay? Finally, in MATLAB, the way to train a network is to use this function here called train network, okay? The three things that it requires are the training data, the structure of this network itself, and the hyperparameters here, the training options, okay? So for the sake of demonstrating here, I'm actually not going to train. It doesn't take very long. I've already trained it earlier this morning. And so this is what you can see in the process of training, okay? So as you train for longer and longer in the x-axis here, you'll see that the accuracy, the blue line here is the training accuracy, okay? And the dashed line here is the validation accuracy, right? So you can see that if the training process is going correctly, both the training and the validation accuracy should kind of match with each other and increase over time, okay? You'll also see the loss curve, right? So the loss is sort of a measure of the difference between what your network is telling you, what your model is telling you, and the actual labels that you know, right? So, you know, if the difference is reducing, meaning going lower and lower, it means your model or network is learning the actual labels, right? So it's doing a better and better job. So if your training goes well, again, the accuracy should go up and the loss should go down for a classification problem. Notice that this particular run gave us a pretty good validation accuracy of 96% and ran for about 11 minutes on my single CPU, right? So even on computers like ours, while we are at home, you can run this kind of a training without needing any fancy hardware, and it should do a pretty good job for this particular problem, right? Depending on your data sets and other problems that you work on, maybe you'll need more powerful hardware, but in this case, it was fairly quick, and I ran this already, so I'm not going to rerun it, okay? But that's really how you kind of train your network by using this train network function here, okay? So I'll go back to these slides here to show you sort of reiterate some of these points. You know, there are these hyperparameters, the number of epochs, the training, the learning rate, and so on that you can specify, and then just call train network with your data, your network structure, and your hyperparameters here, right? You will then see these plots here to kind of track how well your network is training, how your model is training over time, okay? The cool thing these days is there's a lot of data. So the Open Neuro data set that you have that we used here and compute, right, is available in plenty. So this is an NVIDIA DGX box, right? So this is a very powerful graphics processing unit, which can do this training. What took about 11 minutes on my CPU can possibly run in under 2 minutes on this hardware, right? So there's a lot of advances in sort of curating and setting up data, as well as hardware compute capability that is available these days for us. Okay. Now, I'll go back to the code and show you a little more about what happens next, right? So once you finish training, we'll create a trained network here called MRI net, okay? And you can use that on your test data to find out how well your network is doing, okay? So that's what we'll run here. So let me actually rerun this section so that the network is actually loaded. Okay, so I just finished loading the network here, and then I'll rerun this right here, okay? So if you notice, we'll get the accuracy here on the test data right here, and notice that it's pretty good, right? It's 97%. So 97% is the test accuracy, which is phenomenal, right? Without a deep neural network, it would be rather difficult to so easily come up with this level of accuracy, right? You can look at this other very popularly used performance metric called a confusion chart. Okay, so there are functions here called confusion chart where you can plot something like this, right? I'll zoom out so that you can see the entire chart in one view. The way to read this is the y-axis here is the true class and the x-axis is the predicted class. Okay, so what that means is every row here is indicative of what the actual class is, and every column here is indicative of what our network told us. Okay, so for example, um, there were 19 in our test set. There were 19 children in the age of 3 to 5, and all of them were predicted correctly by our model. Okay, there were 16 plus 1, 17 children of age 7 to 12, but 16 of them were predicted correctly by a model. One was incorrectly predicted, right? So this is an error. So anything that's not along the diagonal is an error right here, okay? And so this is a good way to find out exactly which classes or which categories the model is performing badly at, okay? So that is one way of actually evaluating or finding out how well your network's doing. Okay, so sort of just to reiterate, there are several metrics that are possible, but beyond these numerical measures of how well your network's doing, the important question to ask is why is the network or the model doing what it's doing, right? How is it actually making these predictions? And so there are ways to do that as well. And this is the part of the talk where I talk about evaluating this, right? So there are ways that you can visualize what kind of patterns your network is learning. And that way, trying to explain its behavior, right? This method here is something called class activation maps. And you can come up with very interesting visualizations like this one here. It's called a deep dream visualization to better understand what your network, deep neural network, is doing. It doesn't have to be a black box. So based on the kind of patterns you see here, you can kind of understand if it's learning the right kind of things for your data set. Okay. I'll show this in code also. In this particular situation, we won't use class activation maps. We'll use something called occlusion sensitivity, which is another way of evaluating this network. Okay, so I'll rerun this here. You'll notice visualizations like this. Okay, so it should come up any second now. I can go back to the slides because I've already stored some of these images. So you can see things like this, okay? So this is another way of evaluating or measuring what parts of the image are important to make the kind of prediction it's making, okay? So for example, in these two images right here on the left-hand side, both of them are the actual and the predictions are correct, right? It's actually between age 7 to 12, and the network is also predicting it correctly. And the warmer or the more reddish regions here are the regions that the network focuses on more in some way to make this prediction. Okay, there is a little more theory behind it. I won't go into it in the interest of time, but you could think of this as the warmer regions are more important regions for the network to make the correct classification. The cooler regions are not, right? So you notice the 7 to 12, it looks at a sort of a larger, uh, 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 larger regions here, right? But for the 3 to 5 case, it looks only at these central parts of the image, right? And so that way, it can kind of just by focusing more on this section, it can more easily kind of make this prediction in this case. But in this case, it has to look for features all across the sort of slice, right? Another sort of non-medical example for this is if your image is that of a pizza, and if your network has to predict that it's actually a pizza, you know, what this image is showing is that the crust of the pizza is more important than the center, or more important than the toppings, right? So if the network looks at the crust, it can make a better prediction of, or it can better estimate that it's a pizza, right? So these are ways of trying to not let your deep neural networks be black boxes. You can then actually kind of come up with some qualitative and quantitative understanding of why they behave that way. Okay. So this brings me to the end of my presentation, where I'll quickly sort of point out that deep learning is versatile. We've shown you example today of medical image classification, but you can do a lot more here, right? You can do speech recognition, image super resolution, a whole bunch of things, right? Here's an example of this particular university where they use deep learning to reduce the data acquisition time for CT imaging, right? So they use these things, the graphics processing units, to train much faster, okay, using many of them, right? The other point I'd like to quickly mention also is MATLAB's not the only framework that you can do this on. There are several other frameworks up there that you might be familiar with or you might have heard of. But there's this thing called interoperability, where you can import these other models from these other frameworks into MATLAB, and you can export also to all of these frameworks, both export and import, in fact, through this thing called ONNX. Okay, so Open Neural Network Exchange. That's the sort of open format for storing neural networks, and it works with MATLAB as well. Okay, so finally, really in terms of takeaways, deep learning has already advanced state of the art in medical image classification, like we saw today, and segmentation also, right? There are several frameworks and several APIs that you can build these models and train these networks on. It's important for all of us working as researchers in these areas to be familiar with these frameworks, right? And then finally, I think this is the most important message: is deep learning networks don't have to become black boxes. You can look at things like occlusion sensitivity, class activation maps, and so on, to make it more explainable, to make it more, to better understand why they behave the way they do. Okay. So finally, that's it. If you're interested in learning deep learning from a very sort of basic fundamental level, we have a free course called the Deep Learning On-Ramp course. Here is a quick link for you to open it up very quickly on your own computers, and you get a certificate at the end of this, right? Also, all the, in MATLAB, everything that I showed here, right? So now it's completed the occlusion sensitivity for, this age group, and you can do it for other age groups as well if you'd like, right? In fact, this entire code is available on GitHub in this particular group, okay? So it's called MATLAB Deep Learning. If you look within this group, all the code for this particular example, the brain MRI age classification example, is available right here, right? Finally, this is how you can contact me later if you have any more questions after this talk. I'll try to get to questions now. Okay. All right. So thank you for your attention. Let me just open the chat window and find out if there are any questions. I see the feedback link, so thank you for posting that. I don't see any questions in the chat. Let me check the Q&A panel. I don't see any questions there as well. Does anyone have questions that I can try to answer at this point in time? If so, please let me know.
Thank you so much, sir, for this very wonderful session. I'm sure the participants had a lot of takeaways from whatever you covered in the past 50 minutes. As you said, we don't see any questions here. If any participants have any questions, we will give them a couple of minutes.
Yep. So I'm happy to stay here for a few more minutes if there
Yeah.
are any questions. Please do not hesitate to post them here. And if you're not comfortable asking questions at this point in time, I'll just share my screen here and also go back to this slide where you should be able to see my email address. So please reach out to me later if you have questions later on too.
Yes, sir. Yeah. If any of the participants have any questions, if you don't want to ask it here, you can drop an email to Mr. Amit Kamath, and he will be glad to get back to you with whatever queries you have. And a general note to all the participants, the feedback link has been posted here. You can just click on the feedback link and give the feedback. And once you submit the feedback, you will get your participation certificates. And since we don't see any questions coming, I would like to thank Mr. Amit Kamath once again on behalf of the entire team here at St. Joseph Engineering College for agreeing to deliver this webinar on behalf of IIG as well as SJEC MATLAB. Thank you so much, sir, for being with us this morning and addressing all the participants. Thank you so much.
Thank you very much. My pleasure.
Thank you, sir. And thank you to all the participants. We would like to close the session now. And thank you very much, one and all. Have a good day.